Good afternoon, everyone, and welcome to our first webinar in the series where we will discover how to optimize your optical system by using Ansys Zemax. First, let me introduce myself. My name is Disa Sitar. I'm a marketing officer at Infinite Simulation Systems and a moderator of this webinar. But before we start, I would kindly ask you to wait 1 or 2 more minutes for everyone else to join, and then we will proceed. Okay, let's begin. First, very quick instructions on the webinar tool you're currently using. As you can see on your screen, you have different options. On the bottom left, you have option to react during the webinar. On the top right, there are 2 important buttons to mention. One is the settings button, and the other one is a question tab. Important remark here, during the webinar, you cannot unmute yourself. So if you have a question, please feel free to ask, but do so by writing the question down under that question tab. Answers will be then provided after the webinar. Please also know that the webinar is being recorded and will be shared with you together with the presentation slides afterwards. So today I'm joined by my colleague Ekim, who will tell you more about how to use Ansys simulation tools in order to optimize your optical systems. But first, a very short introduction of Infinite for those that might not know us yet. So who are we? We are Ansys Elite channel partner serving the Benelux region with more than 30 years of experience in the computer-aided engineering. We are located in Breda, Netherlands, and in Leuven in Belgium. Our expertise spans a broad range of simulation domains like mechanics, fluids, electronics, photonics, and more, allowing us to support clients across various industries. Our main mission is to improve your design efficiency, to accelerate your time to market, help you to reduce the need for costly physical prototypes, and enabling smarter and faster product development. But that's not all. Beyond distributing simulation solutions, we also offer expert support consultancy, and we do organize tailored trainings where you can learn in practice how to use Ansys tools and how to apply them to your engineering challenges. So that it's all from my side for now. I will slowly give my word to my colleague Ekim. So Ekim, the word is yours.
Hi everybody, my name is Ekim and I'm the optical engineer here at Infinite. So I work with the optical software of Ansys. And often when I tell people that I'm working on optics, people think that I am making glasses, like prescription glasses for people with bad eyesight. Hopefully most of you know better. Optics is much more than just designing glasses. Optics is everywhere around you. You can think of telescopes and microscopes and cameras, of course. You have a camera on your smartphone. There are more examples. In a smartwatch, you have a sensor that measures your heartbeat. In cars, in some cars, you have head-up displays. In the industry, you have sensors that monitor certain things using light. So there are many examples. Optics and photonics is a very wide topic. And in order to simulate and optimize and design all those devices, Ansys has 3 kinds of software. So first we have Lumerical. Lumerical is the simulator of light in photonic devices. So when we have devices that has about the same size as the wavelength of light, you can use Lumerical. We have Ansys Zemax. That is what we are going to talk about today. This is a software to design and optimize optical components with lenses mostly, like cameras and microscopes. And then we have Ansys Zemax. This is a powerful ray tracer, and this is mostly used to simulate the propagation of light in whole environments. So not only the optical components, but the whole environment around it. So Ansys Zemax comes in two flavors. First of all, we have sequential ray tracing. Sequential ray tracing means that the light follows a predefined path. So it goes from surface 1 to 2 to 3 to 4 and so on up until the imaging surface. And this is used to design imaging systems mostly. And then we have non-sequential ray tracing. In non-sequential ray tracing, light can follow all directions. It can go in all directions. It can, for example, scatter around a little bit before it reaches the sensor, or it can just bounce off and not reach the sensor at all. So it can go in all directions. But today we will be focusing on sequential ray tracing only. Non-sequential will be done next week with the SPIOS presentation. So here are some examples of applications of Zemax, of sequential ray tracing. You can design cameras, binoculars, but you can also think of telescopes like with mirrors in it, or scanning beam devices like lithography machines, but also interferometers and beam expanders. So before we continue, we have to ask ourselves what an imaging system is. What does a lens actually do? A lens or an imaging system is a device that makes an image of an object, and it does so by collecting all the light from one point and focusing it on another point on the imaging plane. So even though all those different rays have different directions, they all end up at the same point at the imaging plane. And that is the same, and that's the case for all the points on the object. So designing lenses is all about focusing light. That's it. That's what it's all about. So in an ideal case, this is what a lens would look like. All the rays fall together onto one point, which means you have a very sharp image. But this is not so realistic. In real life, it looks more like this. The rays do not completely converge perfectly, but are rather spread out over a certain small surface. But that's okay. As long as your surface is small, that image can still be very sharp. So before we go to the example of the design of a camera, I want to show some important tools in Zemax that you can use to diagnose problems. So diagnose which aberrations there are in your system, and then you can, if you know which aberrations you have, you can do something about it. So first of all, the spot diagram. The spot diagram shows the positions of the rays on the imaging plane. And on the spot diagram, you see different colors, so different wavelengths. We have blue, green, and red light. And we also have different incoming directions. So here we have one incoming direction, another incoming direction, and a third one. And those different incoming directions are called fields. So we have a spot diagram for all the different fields that we have defined in our system. Next is the ray fan. The ray fan shows the deviation of the tangential and the sagittal rays in your system. So this is for the tangential rays and this is for the sagittal rays. And it shows you on the x-axis you have the incoming position of those rays, and on the y-axis you have the deviation of those rays on the imaging plane. And it does so. We have it for different fields. And the shape of these curves will give me information about what kind of aberrations are present in my system. The point spread function. The point spread function is similar to the spot diagram, but in this case, light is not treated as a ray, but as a wave. When light is very narrowly focused, then ray tracing is actually not so accurate anymore, and then we need to continue treating light as a as a wave. So in this case, it's a sort of spot diagram, but it's determined using another algorithm. The modulus transfer function, or the MTF, this is the Fourier transform of the PSF, and it gives you information about the loss of contrast as a function of the spatial frequency of your object. What do I mean by that? So suppose you have an object like this. It's an array of line pairs. When you make an image of this line pair will become a little bit more blurry. And the amount of blurriness depends on the frequency of these line pairs in cycles per millimeter. So a high MTF is good. That means you have a good contrast, and a low MTF is not so good. That means that means that your image has become blurry. And in the MTF, we have both the sagittal and the tangential direction, and we do it for all the different fields. If everything I've shown up until now was too abstract for you, then you can also do an image simulation. So it will just show you what an image would look like on your imaging plane, and then you can see what kind of problems there are in your system. So in this case, you have a good sharp image in the center, but at the edges it gets very blurry. And here you have a very clear image everywhere, but at the edges it gets quite dark. So Zemax has a built-in optimization tool. So you define what you want to achieve. For example, I want to achieve a smaller spot size for all my fields. And then you can define some variables in your system. So for example, the radius of curvature of your lenses can be a variable, or the distances between the lenses can be a variable, or the thicknesses of the lenses. And then Zemax will make some changes to will automatically make changes to your design in order to improve the optical performance of your system. So I'm now going to show an example of how to design and optimize a camera. This example that I'm going to show is based on an example from this book. It's a really nice book. I really recommend reading it. But my version is a little bit shorter than what is shown in the book. So we are going to design a camera, and we are going to do it on the following sensor. It's a CMOS sensor with the following dimensions, and it has 640 by 480 pixels, which means that each pixel has a height and width of 7.5 micron. We're going to define some specifications for the camera. The camera is going to make images of objects that are infinitely far away. So when something is very far away, then we can practically say that it's infinitely far away. We have a field of view of 50 degrees, and we're going to make images of with visible light rays. So we're going to use 3 colors: red, green, and blue. And we specify that the MTF should be 50% at the frequency of 50 cycles per millimeter. So we start by making a simple sketch of our system. We have here our sensor, and we're going to put a lens here. And we have a field of view of 50 degrees. And using some, so we are going to determine the effective focal length of our system. So we can derive this simple equation using a little bit of geometry knowledge, and then isolate the effective focal length, and then we find out that the effective focal length should be 6.43 millimeters. So now suppose that we have a lens, we have a stock lens that happens to have an effective focal length almost the same as what we want. So we can just make a simulation with that, and then we can already see why it is so important to do simulation. even though we have the required focal length, you see that the spot in the middle is focusing very well, but the spots at the sides are not focusing very well at all. So we can check the aberrations, and as expected, the on-axis field is very nicely focused, but the other ones are not so well focused. You can also see it in the ray diagrams. Here we have it completely flat, which is good, but here we have a curve, a slope. And also when we do an image simulation, you can see that indeed the image is very clear at the center, but very blurry at the edges. And if we check the MTF at the frequency of 50 cycles per millimeter, we see that all those curves are below 50%, which is not good. So what we are going to do is we are going to automatically optimize our system. We're going to specify that we want to reduce the spot sizes. And we are going to define some variables in our system. So here you see that the radius of curvature of the lenses are now variables, the V of variable. And also the distance of the stop surface to the image surface is also a variable. And after optimization, this is what our new lens looks like. It already looks much better at the edges. And we can check the spot diagram and see that the spots are now about the same size. It looks as if it is bigger now, but that the scale of the diagram is changed, so it is the same or even smaller. And that's also the case for the other spots. When I look at the ray diagram, at the ray fan, I can see by the shape that there is a lot of coma in the system. Coma is a sort of an aberration. So we're going to apply a trick to get rid of the coma. Let's check the MTF. At 50 cycles per millimeter, we are still below 50, still below 50%. So a trick to reduce the aberration called coma is to shift the stop. So the stop surface is the surface that limits the size of the light beam that comes in. And if you shift this, if you make it a variable, you can get rid of coma. So we just made it a variable. And then after optimization, this is what it looks like. Again, the spots have increased drastically. The circle that you see here, the black circle, that's the size of the area disk. This is the theoretical limit of how small your spot can get. And you can see that it gets very close to it, which is very good. But we see that there's a lot of so-called chromatic aberrations. So the different colors behave differently. So red, green, and blue all behave differently. So we need to later fix the chromatic aberrations. So let's check the MTF at 50 cycles per millimeter. We are still, some of them are close to it. One is even above it, but these two are still way too low. Yeah, so chromatic aberration. What is a chromatic aberration? Chromatic aberration means that different colors do not focus at the same focal plane, as you can see here. And this is what an image looks like without chromatic aberration, and this image has a lot of chromatic aberrations. You can see these rainbow colors here. All of this is caused by chromatic aberrations. In order to reduce the chromatic aberrations, we are going to make a so-called achromatic doublet. We're going to add a flint glass to our lens. A flint glass is a sort of glass with special optical properties which can help reduce the chromatic aberrations. So we just add a new glass to our design. It is the new glass is called NSF4. And then we just optimize it again. And this is what our design looks like after optimization. You can see that the spot size has increased there drastically. And also you can see that the chromatic aberrations have reduced. There's still some here, but it's already looking much better. You can see that in the X, there's no deviation in the X direction, but there's still some deviation in the Y direction. Let's check the MTF. These three are looking very good, but these are still below 50%, so we still have some work to do. This is a tool that I have not shown you. It shows you the amount of field curvature and distortion in your system, which are also aberrations. And we can see that we need to do something about the field curvature. So what is a field curvature? A field curvature is a sort of aberration. That means that the light is not focusing on the imaging plane, but it is focusing along a curved line. And in order to get rid of field curvature, you can add the so-called field lens, and because of the field lens, the light will now nicely focus on the imaging plane. So let's do that. Let's just add a piece of glass to our design, close to the sensor. And we don't define any curvature yet. We're just going to make the curvatures a variable and let the optimizer find an optimal design. So we optimized our design, but now we have a problem. You can see that the first surface is passing through the second one. This is not realistic. This cannot happen. So we need to go back to our optimizer. And also another problem is that the field glass is touching the sensor, which is actually not good because it can damage the sensor. So we go back to our optimizer and define some constraints to the sizes of our lenses and also to the edges of the lenses. And also what we are going to do is we are going to add more variables to our system. So the more variables we have in our system, the easier it is for our optimizer to find an optimal solution, even though it will take a longer time now. And this is what our design looks after optimization. It has changed drastically, but that is okay. That is good. Let's now check the results. All the spot sizes are now well below the area disk size, which is very good. And also the aberrations have reduced drastically. Again, it looks like there are a lot of aberrations, but the scale of this plot has changed. And let's check the MTF at the frequency of 50 cycles per millimeter. We are now well above 50%, so we have reached our targets. So this is the design that we started with. It was very blurry at the edges. And this is what it looks like now. It is much clearer now, although we have a little bit of dark spots at the edges now. So we can continue optimizing it to get rid of this problem. But for today, we are happy with it, with the results. So we will wrap up and I will give the word again to Tisa.
Thank you, Ekim. I hope everyone enjoyed the session, but before we officially say goodbye, I would just like to remind you and invite you, Ekim, next slide, to join us for the other two upcoming webinars in this webinar series. You can already register by scanning the QR codes you see on your screen, but if not, no worries, because the registration links will be shared with you in the follow-up email you receive afterward, including the recording of the webinar, the presentation slides, and we also received some questions asked during this session, and the answers will be also provided in the same email. So that's everything for now. I wish you a great day ahead, and thanks again. Thank you. Bye.